I think that exploring space is a cultural activity. It's much more than just science for science sake. And this is an important point for both the scientists and for the public to realize. When Armstrong stepped out on the moon, 500 million people watched him in real time, and the moon all of a sudden became a familiar place. When Mariners 4, 6, 7, and 9 photographed Mars, it was grasped away from science fiction and put into the role of science. And it was a real place, although very strange. It remains very strange. When Mariner 10 went to Mercury and photographed it for the first time, Mercury entered from the domain of obscurity, just nobody even knew it was there really, into at least a real place with features, with a surface, and a character of its own. As a consequence, in this last decade really, the volume of space that exists in the mind of men all over the world, millions and millions of men, has expanded.
Mercury, as seen through the best Earth telescope. Venus. In '62, these were the best photos of the planets we had. Mars. We had no knowledge of what features lay on their surfaces. We didn't know their ages. Had they formed at different times? The last 13 years has changed that. There's been a celebration of US and Soviet rockets to the planets. Beginning with the Russian mission to Venus in 1961, it accelerated to a crescendo in the spring of '74 when there were 6 rockets simultaneously traveling out from Earth. The planetary exploration was paralleled by Apollo, man on the moon. Apollo began from a political decision to get a man on the moon before the Russians did, specifically by 1970. They did that. Now, with the rationalization of hindsight, their trips to the moon have turned out to be the key to understanding the planets. The U.S. National Aeronautics and Space Administration, NASA, has evolved 2 major scientific objectives for its research in space. 1, to seek out how life began. Secondly, to seek the origin of the solar system. The prime tools of planetary exploration are precision television cameras. These are 2 about to fly to Mars. They're made by craftsmen, each contributing something of his own design to the component he makes. Sculptors carving from solid lumps of metal. The cameras are on their last test before being fitted to the spacecraft. In a vacuum chamber, they're being checked to see their optics will not go out of focus in the temperature changes they'll experience when they're launched into space. They'll send their pictures back as a set of numbers, each number representing one of 256 possible levels of brightness. A computer converts each number to an appropriate dot of grey, and 500,000 dots build up a picture. A photograph can only show 10 shades of grey, so the numbers hold much more information than the picture you're looking at now. This picture can be reprocessed so as to reveal only the fine detail. These are some of the thousands of pictures from the mission to Mercury. With the arrival of the pictures, analysis begins. This machine compares two pictures of the same object taken at different times during a mission. It allows contours of a mountain to be plotted directly. The thousands of pictures are all individually studied and their information blended together in maps. NASA has created an information explosion. These maps are a complete contrast to the fuzzy blobs of 13 years ago. Then there were hundreds of theories of the origin. Some saying the planets were the debris left after our sun had collided with other stars. Some that the planets and sun condensed from a cloud of gas. The trouble was not finding a theory, but finding one which was not totally improbable. NASA's philosophy has been to visit as many planets as possible to find the facts, to find out what theory has to explain. What story of the origin can we tell after 14 years of exploration? The search begins before men landed on the moon. The question then was, what was the cause of the craters there? Most people were sure they were volcanoes. But 15 years ago, in a field of volcanic craters in the Arizona desert, a study was begun. It was to prove this crater was not volcanic at all, that it was caused by the impact of a meteorite 24,000 years ago. The scientist who's made the most intensive study of meteor crater and the expert on impact events is Dr. David Roddy.
It's really quite surprising to me that as early as the mid-1950s, Meteor Crater was still considered to be a volcanic crater by a certain part of the scientific community. It's enough to blow your mind, but there were serious papers still being written at that time. But with the advent of the space program and the large amount of research that's been dumped into those kinds of areas, we've come to a point where we have enough physical data in which we can tell quite clearly the specific diagnostic criteria that tells us whether this is a volcanic crater or whether this is a meteorite impact crater.
The laboratory experiments that led to understanding what happened during an impact were done by Don Galt with this gun. It fires small aluminium spheres. They simulate meteorites at speeds upwards of 20,000 miles an hour. The complexity of the gun is because the impact takes place in a vacuum. The angle of the gun can be varied. For the experiment we're about to see, it's a vertical impact into this box of sand. It's filmed with a high-speed camera, expanding 1 second into 5 minutes. Experiments and Roddy's fieldwork established how impact craters form, how they can be distinguished from volcanoes. It was Roddy who instructed the astronauts, and these are the actual diagrams he used. The meteorite would vaporize, and the floor of the basin would be flung into the air as large chunks of rock. The cone of surface material would flop over upside down, forming a raised rim, and the blocks of rock would rain back, creating an outer ring of secondary craters. The features were recognizable in the moon craters seen from Earth. So before man went to the moon, telescopes had confirmed that a few of those craters down there were caused by impact. The astronauts produced two very important results. The first was how many impacts the moon had received. In this dramatic piece of film, the lunar exploration module of Apollo 17 is just skimming over the tops of the lunar mountains on its last orbit before landing. On board, the last man on the moon, incidentally the only geologist to go there, Harrison Schmitt.
This bombardment was unbelievably intense. It's something that is almost beyond the comprehension of people, even geologists to a large degree. The surface of that moon, the light-colored surface you can see on a full moon, even now, was saturated with craters, with impacts capable of forming craters, say 100 kilometers in diameter. Saturated. Every point on that surface was hit with that size of an impact. After this time, after around 4 billion years ago, there was a period when there were a number of very large impacts large enough to form basins up to 1,000 kilometers in diameter. Now, this appears to be a very distinct and different period of bombardment. We don't understand why, but it is distinct.
The moon had been pulverized to a depth of 6 miles. The bombardment ended with impacts of an incredible size. The Imbrium almost split the moon in two. The second thing they did was to bring back rocks so that the events on the moon could be dated. The man who pioneered the chemical techniques necessary was Jerry Wasserberg.
Well, since we're mostly investigating extraterrestrial materials, and we have to worry about terrestrial contamination, in some cases, the total sample just weighs 1/1,000,000th of a gram. So we have had to develop manipulative procedures and standards of cleanliness which permit us to handle these materials a single grain at a time, frequently much smaller than a grain of salt, and analyze that rather than our own droppings.
Wasserberg's team measure how long it is since a rock was last molten, since it solidified. Moon rocks are a mixture of the powdered remnants of earlier rocks. Rocks that can be of such different ages that dating the whole sample would give meaningless numbers. That's why the natural cement is shattered so that some of the individual sand-like grains come free.
You can put it down.
Nothing in this laboratory is ordinary. That's not paper, but a very special plastic. The air is filtered. All surfaces covered with unchippable paint. Everything is wrapped till needed. Just those pieces which might be individual crystalline grains are sieved through, and finally they're picked out by hand. Each of the little grains is going to be dated from its content of lead, thorium, and uranium. The ratios of those 3 trace elements give the age since it solidified. Dissolved in acid, the grain goes into an ion exchange column that allows the chemicals through at different speeds. Experience tells them when the lead comes through. By catching just the right drip, he catches the millionth of a gram of lead he's looking for. That drop is gingerly put onto a heated wire. Gingerly, for to get that drop has taken 3 days' work. Finally, that wire is heated in a mass spectrometer, which flings the atoms down a tube where a magnet sorts them out and electronics count them. From here, it's arithmetic to calculate the ages. They're reaching back through long periods of time. 1,000 million years is given a technical name, 1 eon. The measurements show that all the material in the solar system is the same age, precisely 4.6 eons. The cratering began between this and 4 eons ago when it ended suddenly. The final big impacts were at 4 eons. Then came floods of lava rising from the interior of the moon. Since then, very little change at all. 10 or so craters like Copernicus and Tycho. This is what the moon would have looked like 4 eons ago, after the bombardment. Then the lavas flooded out. And since then, very little change apart from the dozen or so craters and the lavas changing to lighter grey. The next question was, is that bombardment something particular to the moon, or had it happened to the Earth as well? We couldn't know. Until recently, our oldest rock was from Minnesota. The oldest so far from Greenland. So we couldn't tell because on Earth we don't have rocks old enough to record the bombardment. So the question still was the cratering record special to the moon, or perhaps waiting to be read on the other planets? If it was, would it be the same story or a different one? The space missions were to answer that. But first, what's the scale of the solar system? Suppose the Sun to be 7 feet 6 inches across. At this scale, Mercury, a pea. And it's 36 million miles from the Sun, 100 yards. Next planet, Venus, a walnut. It's 67 million miles, which is 190 yards. Earth and Moon, only 240 yards. Mars. 142 million miles becomes only 400 yards, a quarter of a mile. Massive Jupiter, a 9-inch cabbage. Now we move out to a different area of the solar system. 486 million miles are represented by 1,500 yards. From here on, distances are vast. Saturn would be at 1.5 miles. Uranus 3 miles, Neptune 4 miles, Pluto 7. 1971, the Mariner 9 spacecraft arriving to be launched to go into orbit around Mars and map it systematically. There'd been 3 previous flights to Mars, flyby missions. They'd seen moon-like craters as they zipped past, taking their strips of photographs. There were suggestions Mariner 9 should be cancelled. The answer was already known. Mars had craters. What was the point of looking at another moon? But they did go. In fact, it was to have been preceded by Mariner 8. A member of the TV team was Bruce Murray.
Mariner 9 was the geologist mission, and Mariner 8 was the meteorologist and the astronomer's mission. Except fate has a nasty way of interfering. Mariner 8 ended up in the Atlantic Ocean. There was a failure of the launch vehicle. And so these things have to be done very quickly because there's only a few weeks that one can launch at any particular opportunity to Mars. And we had to go with one space vehicle, Mariner 9, and had to somehow compromise the two. As it turned out, Mariner 9 proved to be an extraordinary exploration mission. I think it was the most astounding mission perhaps the United States has flown to date in many ways, because of the nature of the discoveries that were found. There's been a profound and I think irreversible cultural change brought about by the very act of space exploration and by having it well photographed. It means that the photographs could speak for themselves, not be interpreted through the jargon of science.
As Mariner 9 approached Mars, a tremendous dust storm broke out, covering the whole planet with dust 50 kilometers up into the air. As the spacecraft came in, all that the television team could see were these 4 dark spots, christened Groucho, Chico, Harpo, and Zeppo. Embarrassed and to fill in time, the team turned the cameras onto the two Martian satellites, Deimos, the outer satellite, 10 miles in diameter, and Phobos, 20 miles across, both battered by billions of years in space. The storm lasted 30 days. Then, as the dust started to settle, the spots became darker and darker. There was mounting curiosity about what they could be. Then the Marx brothers' heads broke through. Immediately, two geologists, Mazursky and Macaulay, guessed they were volcano tops. The others were skeptical. When the dust did finally clear, there was no doubt. Groucho turned out to be the biggest volcano known in the solar system, 17 miles high, more than twice the height of Everest. Hal Mazursky, leader of the Mariner 9 TV team, now heads the committee selecting the site for the two Viking spacecraft that will land on Mars in 1976. Viking will search for life. It'll analyze the Martian soil for microbes and radio its answer back. Mazursky has to decide where they'll land and search.
What is the best place on Mars to land these very few spacecraft? We only have two. We've got a very complicated, very large planet, so we only have two chances to find the right information. The interesting thing about the volcanoes is that's where the atmosphere comes from. That's where water vapor comes from. That's the clue in the search for life. Well, that was our first requirement, that the planet be hot in the interior and the juice coming out of the volcanoes. The second problem is what happened to that water vapor after it came out. And we looked carefully at the pictures and we found that in this region there were a number of great stream channels that started in this country. They start in great masses of collapsed debris. And one of the ideas is that Mars warmed up and melted the subsurface ice, caused the collapse of the great masses of debris. Then the water flowed out downhill into the northern lowland. So our Viking landing site is obviously here, right at the mouth of these largest streams on Mars. In addition to the great conglomeration of channels that flows into the northern lowland, in other parts of Mars we have quite different kinds of channels. In this region, in the smooth uplands, is quite a different kind of stream channel. There are dozens of little tributaries that come together, and here it looks as though we have to have had water falling out of the Mars atmosphere and hitting the surface, collecting together into these little streams and flowing down this sinuous channel. All through the central upland of Mars, in every sloping surface, there are hundreds of little tiny microchannels, just a hundredth of the size of the ones we've been talking about. And this map was prepared for the Soviet Union. They tried to land on Mars earlier this year, and their landing site was right in the middle of this region that has dozens of these little tiny microchannels in it. They didn't successfully land. That was their fourth attempt. The lesson to us is that Mars is difficult to land on, so we really have to be prepared for our try in about a year and a half. What we found out from detailed examination of these three different kinds of channels is that some of them are very old. They have many craters that have struck them, and the sides are eroded and degraded. Others look brand spanking new and fresh. So we think that not only did the Mars climate have to have been different one time in order to form stream and have water flow on the surface, but it has to have been that way dozens of times in the past. Do I think that the most probable explanation of the stream channels is that water rained and flowed on the surface? The answer is yes. I think of the various choices we have, that's easily the best one.
A wind tunnel experiment at the University of Santa Clara, California. Ronald Greeley is trying to explain a unique feature on the Mars surface. He's looking for an explanation of a long black plume that stretches 60 miles. It obviously begins from a crater. And in the bottom of the crater he finds an intense dark spot. His theory is that this might be a volcanic source. So he set up in the wind tunnel a model crater into which he could introduce sand. He would let it drift downwind and film the pattern that would result. The plumes match. That suggests that there's at least one active volcano on Mars throwing its cinders across the surface. Jack Macaulay was senior geologist on the Mariner 9 team. He's been trying to understand this Martian feature, here dimly seen through the dust, but 40 days later seen to be two deep, rugged valleys. All the geologists were excited to see something familiar in the cliff edge, the big bite of a landslide, but dramatically bigger than any landslide on Earth. These cliffs are 4 miles high. This model of the canyons was made by NASA. Its accuracy has been approved by NASA's higher brass. This is what it would be like to swoop down into that vast canyon system. So deep, the Alps would get lost down there. Barely reaching halfway up the cliffs. It's called the Euphrates Canyon. It's 3,000 miles long. It's 150 miles wide. Macaulay believes it began from a fault crack. There are networks of cracks on Mars's surface near the canyon. They're very similar to fault cracks on Earth, the result of tension pulling the surface apart. He believes that there was erosion of the exposed cliff faces. As here in the Arizona desert, this cliff is retreating as wind and water wear it away. To get some sense of scale, Euphrates is more than 100 times bigger than this, the Grand Canyon. The Grand Canyon, after its initial opening, is being widened by erosion. On Earth, the erosion is primarily by water, but helped by the wind. On Mars, the erosion is by wind alone, a fierce sandblasting by the thin wind at 400 miles an hour. One of the members of the TV team of Mariner 10 is a British scientist, Dr. John Guest.
It's interesting on Mars that the volcanoes tend to form some kind of a pattern. We have these 4 major volcanic structures running in this direction. They're in a straight line and must represent a fundamental structure in the Martian crust. And then we have this great Euphrates chasm running through here, another major structure in the crust. The planet is splitting apart there, forming a great tectonic fracture. Possibly the kind of thing that one could imagine if one was seeing incipient plate tectonics, where one plate is beginning to break away from another point.
The new dominant idea on explaining the major features of the Earth is so-called plate tectonics, or continental drift. And this invokes the idea that at one time all of the continents on Earth were joined together. And then about 200 million years ago, they broke apart and are drifting slowly over the face of the Earth. What this says is that Mars, in its present shape, is very much like the Earth was that 200 million years ago.
I think we've seen a sort of revolution in the earth sciences with this increased knowledge of the planets, because the other planets appear to have preserved a period of their history which is before a period that we can recognize on Earth.
Quite unexpected by the scientists, they saw the beginnings of continental drift as it may have happened on Earth 2 eons ago. Mars, and so it turned out, each of the other planets seemed to be a snapshot of some stage in the Earth's early history. That's a curious thread in this story. So Mariner 9 was worth sending. It did more than confirm that there was a cratering record on Mars. That record on Mars was like that on the Moon. One feature that was seen on the maps that had been too big to see on the photographs was an enormous crater, like the big Imbrium basin on the Moon, the Hellas basin. 1973, Mariner 10. Venus was to be visited on the way to Mercury. No one has seen the surface of Venus because it's continuously covered in cloud, a haze of sulfuric acid droplets floating in a dense atmosphere of carbon dioxide. At the edge of the planet, Mariner 10 could just pick out a layered structure in the acid clouds. But when photographed through ultraviolet filters, a pattern showed up. During the approach, Mariner 10 took mosaics of pictures every 2 hours. Bruce Murray and his team processed them all so that they would be the same scale. Then they filmed the 40 pictures, assembling what's known in the business as Bruce Murray's creaky movie. It shows 4 days of weather condensed into 6 seconds. The surface temperature of Venus is 480 degrees centigrade, enough to melt lead. The temperature is due to the mighty Venus atmosphere, allowing heat in but not letting it escape, a runaway greenhouse. The interesting evolutionary question is, why are the atmospheres of Venus, Earth, and Mars so different? Scientists can see the surface with radar. They claim to recognize craters that might be volcanoes. It's from that surface that the atmosphere would have evolved. The atmosphere came out when the solid core melted. The temperature then of the bare surface would have been just about 80 to 90 degrees. As the carbon dioxide and water accumulated, the greenhouse effect quickly raised that temperature to 300 degrees, so no water could possibly condense, and the carbon dioxide continued to build the thick, hot atmosphere we see today. On Mars, it was different. So far from the sun, its temperature was below the freezing point of carbon dioxide and water. Both froze instantly. So Mars's atmosphere is there, but frozen down. Mariner 9's monthly observation of the Mars South Pole showed it was made out of a mixture of water ice and solid carbon dioxide. During the first 2 months of the spring, it shrank rapidly as the carbon dioxide evaporated. It left only the permanent water ice, which didn't shrink during the summer. On Earth, our atmosphere started to come out when the Earth's bare surface had a temperature of 3 degrees, just above freezing point. The water condensed, beginning the sea. The carbon dioxide would have begun to heat that surface with a greenhouse effect, but, a very big but, it didn't get far enough to boil the sea because the hot liquid water converted the carbon dioxide into carbonate rocks, into massive beds of limestone and chalk. If it hadn't been for the liquid water, all the carbon dioxide would have stayed free. Venus and Earth have the same amount of carbon dioxide. The nitrogen, a 1% trace in the initial volcanic gases, accumulated as a thin remnant of what was potentially our massive atmosphere. Had Earth's initial temperature been just 5 degrees centigrade higher, that is, had we been at 89 million miles from the Sun instead of 93, the greenhouse effect would have boiled away the water and our Earth would be as hostile as Venus. So Venus shows us Earth as it might have been. After Venus, Mariner 10 continued on to Mercury. This was all we knew then of Mercury's surface. There were different views among the team of what they would see. Some thought it would be cratered like the Moon. One thought that Mercury was small because the sun had boiled its surface off and he was expecting to see a blasted wreck. Others that Mercury had an atmosphere whose violent action would have scoured the original craters away.
We switched the cameras of the spacecraft on about a week before we encountered the planet. The first thing we saw was just a small disk with a white spot on it and very little else. But nevertheless, we started discussing what it might be that we were seeing and going to see. And then every day after that, at midday, we'd switch the cameras on again. And then about 2 days before the near encounter, we thought we were recognizing craters on the surface. At that time, we had a suspicion that we were looking at a planet that may well look like the Moon. And then the spacecraft got closer. We swooped past the planet at about 11 kilometers per second, taking pictures all the time. And this great flood of data came back, covering everything that could be seen by the spacecraft. It was almost as if somebody had arrived with a great lorry load of pictures and dumped them in our office.
The surface was exactly like the Moon, difficult even for an expert to tell the difference. It meant that Mercury's skin is the same as the Moon, a light silicate. But Mercury is the densest of all the planets. It couldn't be light silicates all through. Beneath that crust must lie a massive iron core, at least 80% of the planet's diameter. At some time, the whole planet had melted, and as slag rises and floats on the iron in a blast furnace, so the surface had formed on top of the molten interior. That surface was cold before the bombardment ended. It had to be solid to preserve this cratering record. So Mercury melted and stopped there, a snapshot of what Earth was like sometime before 4 eons ago. As Mariner 10 left Mercury, it saw on the other face a huge impact, half in shadow. It's filling your screen now. The curved ring of mountains is the crater rim surrounding the lava-filled interior. Mercury had had its gigantic impact too. Again, the crater record showed what had happened to the Moon had happened to Mercury.
Oh, I think the neatest thing that happened was when the Mercury photographs came back, because and even Mars for that matter, because we were seeing cratering on not just the Earth and the Moon, but on Mars and on Mercury. And I think we can very, very safely predict we'll see cratering throughout the entire solar system. The most fundamental and most interesting thing to me is that we are working on a particular process that we know should be operable throughout not just our solar system, but throughout our galaxy, throughout all of space as far as we're concerned.
1972, Pioneer 11 out from Earth passes the Moon heading for Jupiter. As the spacecraft approached, the colored bands and the red spot could be seen. Pioneer 11 confirmed what Pioneer 10 had discovered on the first visit to Jupiter a year earlier. The planet was giving out 2.5 times as much heat as it received from the sun. The explanation most favored was that the heat is produced because Jupiter is still contracting out of the original cloud of gas. So the snapshot is not so much a planet, but of a forming sun. Scientists see suggestive parallels between Jupiter and the origin of the solar system. There is one theory beginning to be discussed in scientific circles. It's very tentative yet, but it does explain the cratering record and why planets near the sun are dense and those far away made of light materials. It's thought the planets evolved from one cloud of gas. 98% would have been hydrogen and helium, but there would be traces of iron, silicon, rock-forming materials. In the gas, there would be chemistry going on as atoms banged together, creating many compounds. The molecules stuck together to form tiny grains. They grew quickly to the size of a small pebble. But they didn't get any bigger. Because of the gravity, they started to settle to the plane of the nebula, a flat sheet, exactly like Saturn's rings. They couldn't fall inward to the sun, because, like the rocks in Saturn's rings, they would be orbiting around it. So, in a few million years, much of the gas would condense to a flat disk. But this disk didn't have a uniform composition. What grains can condense depends on how close to the proto-sun they are. Close to the sun, just the rocky material would condense. Iron and silica by the orbit of Mercury. Next, perhaps iron sulfide, say, by the orbit of Venus. And further out, water ice. Further out still, carbon dioxide ice. Beyond Jupiter, the hydrogen and helium would condense. Only the small amount of rocky material had condensed out at the center. Towards the edge, everything had solidified. What happened next was that the disk broke up because it was gravitationally unstable. The pebbles condensed to lumps about 5 kilometers in diameter, each weighing about 100 tons, rather like the asteroids. Now, these bodies started collecting each other up through collision. It's this history of impact we may be reading in the cratering record. So, in the end, the planets formed. Those near the Sun, the inner planets, were the trivial amounts of rocky silicon, iron, and aluminium oxides. The outer planets big, cold enough to condense all the ices and gases of the gas cloud. At this stage, the inner planets were still moving in the hydrogen and helium. It's presumed that the Sun became super hot and its solar wind increased tenfold. That blew the uncondensed gas away. And that's how we find the solar system today.
The interesting feature that comes out of this picture is that the most volatile substances we find on the Earth are the substances that condensed somewhat farther away from the Sun than where the Earth is now. In fact, these are substances that were coming down.
Gene Schumacher has been trying to understand how planets finally formed.
Water ice is particularly important to us. Carbon dioxide ice is another. These materials were condensing out about 2 to 3 times as far away from the Sun as where our Earth is now. But those particles, those planetesimals, which grew out of particles condensed to that distance, were very close to Jupiter, and they were perturbed very greatly. In fact, most of them fell on Jupiter, but a small fraction fell on the Earth, and that's where the water and the carbon dioxide that's now on our Earth, making up the oceans and contributing to rocks in the crust, that's where most of that material came from. The substances, carbon, oxygen, hydrogen, that we now find on the Earth, actually were perturbed by Jupiter from a distance about 3 times as far away as we are, and fell on the Earth last, sort of plating the Earth and giving us the substances that have now formed life. That's why I'm able to stand here and talk to you today, because of old Jupiter that was formed out there.
One of the major problems which we have in the origin of the solar system is to know the particular types of material from which the solar system was constructed. And now many of my colleagues and I are obsessed with attempting to identify those particular mineral species which were present in the interstellar medium, dust grains, which were then aggregated to form the solid bodies of the solar system. And the hunt is on. I don't know how lucky we'll be in finding them, but I think it's quite clear that from the work done here by Lee and Papanastasiou clearly have identified relics of the interstellar medium that we can now handle in our hands, sort of with tweezers in the clean room. Now, which stellar objects fed the solar system? What are the true materials which are identifiable as an interstellar grain is what the great hunt is now. I thought last week for sure we were going to find one this Monday. I'm not that sure today, but next Monday we'll still be looking.
During the last 2 eons, the moon has had a dozen or so impacts about the size of London. We now know these impacts aren't special to the moon, but are universal. So the Earth should have had some too. What would an impact be like if we had one in the Atlantic tomorrow?
The order of magnitude calculations would suggest that if you had a vertical impact in, say, the central part of the Atlantic Ocean, you could expect a tidal wave, initial wave around the crater, that is what you'd call the crater rim, which would be transient, of course, that would be on the order of probably 10 to 20,000 feet high, which is a speculation in terms of the actual height of it, but the numbers are impressive if you can make the direct analog calculations, which are reasonable, and we're only interested in ballpark. And imagining a wave in a transient body, such as water, moving up to, say, even a couple of miles in height, and then imagine the tidal effects that you'd have from that quite clearly. If we were to have an event such as this, the tidal waves from that would extend all the way across the ocean, and of course they would wash the seaboards of both the continent, Great Britain, and of course the North American coast. And this is not a statement to cause one concern, but there are bodies of this size passing the Earth. The so-called Apollo asteroids, for example, are in Earth intersecting trajectories. They have diameters on the order of several miles to 12, 13, 15 miles across. These are super bodies. If we would have a collision with such a body of this size, I think one would expect both atmospheric effects and terrestrial effects that would truly modify the entire climactic pattern and the life ecological systems that we see at this present time.
10 years ago, an asteroid, Icarus, passed within 4 million miles of the Earth. 40 years ago, Hermes came closer than the moon. Now geologists are beginning to find some Earth structures are best explained as impact craters. It's something new in geological interpretation. About 100 craters have been positively identified, and a new one is being discovered every year. But instead of the 50-mile basins, think of those big ones thousands of miles across, the enormous impacts of 4 eons ago. Did we have one?
Suppose an impact happened on Earth as large as the one that produced the Caloris Basin on Mercury, or the Imbrium Basin on the Moon, or the Hellas Basin on Mars, for example. That would mean that the size of the impact was 1,000 to maybe even 2,000 kilometers in diameter, that the depth was 100 or 200, maybe even 300 kilometers deep initially before it started to rebound. What would happen, a lot of things would happen, obviously. Obviously, it'd be kind of tough on anybody living around there. But what would happen that might have lasting consequences is that the material, which had originally been 200 or maybe even 300 kilometers deep, is now brought to what becomes the surface. The pressure on top of it is relieved. Now, the rocks of the Earth are very sensitive to this, and different reactions take place at different pressures and temperatures. And so by taking material that's originally very deep and then bringing it immediately to the surface on a large scale may trigger some reactions, some chemical reactions, which otherwise would not happen. It's possible something like this was the beginning point necessary to start the growth of continents.
What space has done for geologists is to give them a new perspective into the past, put in context the small piece of Earth's history they knew. For us, we have become increasingly aware of our fragility, of the knife edge of chance on which our continents and our atmosphere depended.
There's no economic value to go to the moon. There's no economic value of going to Mars. It's not utilitarian in that sense. It's cultural. It affects the minds of people. If material necessity were enough, the United States would be a very happy and passive place. It's not. And so the parallel issue of our times is a framework, a reference, a set of values, a perspective on man's existence. That's where space exploration is important, not in material necessity.